We're now going to dive into the bits and bytes that make up an actual packet, at least the part that is the payload and the TCP header on front of that. We'll focus on the TCP header. The TCP header can be described by this sort of picture that is like the RFC diagrams that we saw before. In this picture, we show that the TCP header on the TCP segment, the application's data, together with the header makes the whole segment. But the TCP header starts with a source port number and a destination port number. And each of those numbers is 16 bits, and so they take up a whole line in this picture, where each line is 32 bits of header information. We're going to skip over these flags for just a moment and focus first on head length here. This is 4 bits sitting after 3 32-bit words. That length describes the overall size of this yellow region here in terms of 32-bit words, how long it is. The reason we need this header length is because there are some options here that may or may not be present. That's why we've got the zigzags on the side. So if there are 0 options, which is typical, then the number here will be 5, because we have 1, 2, 3, 4, 5 32-bit lines in our picture. After the header length, to fill out some of the bits in this same line, we have some flags that we're not going to talk about, like CWR and ECE, but these have to do with packets that are there for congestion notification. RST, SYN, and FIN, SYN and FIN we're going to talk about more later, so you'll see how these bits get set in a protocol. RST we won't talk about so much today. We will also talk about the ACK bit that's sitting in there. The receive window we'll also say more about, but the receive window in a packet is for one end of a connection to tell the other end of the connection how much data it's willing to receive right away. And we include this information in every packet, and that helps with flow control overall, as we will see. There is a checksum field in the header that helps detect corruption so that corrupted packets can be ignored. This checksum is formed by adding up all of the 16-bit words and the TCP header, as well as the application data. And the TCP protocol specifies specifically that we take the ones complement of that sum. That means the other end can start with this checksum and then keep adding all the things that it sees, and it should cancel back out to 0. If it doesn't, then that means the packet is corrupt. After the source port and destination port in the header, we have something called the sequence number. This sequence number corresponds to bytes that were sent previously by whoever sent this packet. So if this packet is coming from the client, that is the number of bytes that the client has sent previously, not counting the new bytes here. That sequence number will be important to the other end, to the receiver of the packet, to know whether they got all the data that was meant to be sent before this data. At the same time, when the ACK bit is set here, then there's an acknowledgement number that's the complement of that. That is saying how many bytes the sender of this packet has received in the connection from other packets from the other end. So we'll see that sequence number and acknowledgement number work together to keep things in sync. Again, this acknowledgement number represents all the bytes received so far. You could also think of this acknowledgement number as a number associated with the next byte to be received by the sender of this packet, to say which number byte that should be. And what this represents then is a cumulative acknowledgement, because it's telling the other end, the receiver of this packet, how many bytes have been received as opposed to sent. If we consider the two hosts that are involved then, it doesn't matter which one was the client and which one is the server, so I'll just call them A and B. Then every time A sends packets, the source and destination port are one way around, and packets sent by B will just be the other way around. The same port numbers just flipped. Similarly, the sequence number on one side corresponds to the acknowledgement number on the other side.